lecturer this morning is Professor Tolley. He's going to continue his work on Galilean massive gravity.
Okay, thank you. So I'm just going to review a little bit what I've discussed about up to now. And in particular, yesterday I was discussing how in any generic theory of massive gravity, and I don't just mean the specific, what you might call hard mass gravity, where you have a single graviton given mass, but even things like the DGP model, these extra dimensional models, the deconstruction framework, and then I talked about new massive gravity in 3D. So all of these different theories in which effectively the graviton acquires a mass, or there are gravitons in the system that acquire mass, in some limit, if you take the massless limit of that system, then you recover the Galilean. And the essential reason for that is this representation theory decomposition, that a massive spin 2 field in its massless limit splits up into a massless spin 2, or really helicity 2, and a massless helicity 1, and a massless helicity 0. And in 4 dimensions, that's 5 degrees of freedom split up into 2, 2, and 1. And the precise decomposition is that the massive tensor, if I describe it by a capital H here, big spin 2, splits up into the massless spin 2, and then the canonical normalization is by the Planck mass in d dimensions as d minus 2 over 2, plus then the vectors whose presence are, which play the role of the Stuckelbergs for the broken linear diffeomorphisms. These being vectors, they're the helicity 1, helicity 2, helicity 1, and finally a scalar piece, which is the Galilean cloud. And so this is called the Galilean because it exhibits this rather trivial symmetry, pi goes to pi plus a constant plus v mu x mu, under which symmetry the double derivative of pi really maps into itself. And any scalar field with this symmetry is called a Galilean. Just because this symmetry looks analogous to what we normally think of as the Galilean symmetry, the non-relativistic limit of the Lorentz symmetry. And so generically we get, so we always get this. So this was shown, originally this was discovered in the context of the DGP model, and then since then it was shown to arise in new massive gravity, and also in the other massive gravity theories that I'll talk a bit about later, and Rachel is going to talk more about as well. So this is really a generic phenomenon. That's the idea I want to get across. Now the other key point is the normalization here. Here I put in scale so that these fields are canonically normalized, at least up toward effectors of unity. And this limit we're taking, which is the massless limit, m goes to 0, in that limit, this thing is clearly going to be bigger than this and this, because you've got a 1 over m squared here, and a 1 over m there, and no m's there. So as m goes to 0, this thing will be the dominant piece. So that means that in the massless limit of a massive theory, the dominant interactions come from the Galilean itself. And just looking at this normalization, you'll see that they will come in at a scale which we usually call lambda, which satisfies this relationship. And typically we have in mind that the graviton mass is very small, certainly much smaller than the Planck scale, but in usual cosmological applications of these theories, we don't have to go there, but we're imagining this is order Hubble scale. And so lambda is some scale intermediate between the Planck scale sitting up here, and then the graviton mass scale down here, and then depending on the dimension, there's this new scale lambda intermediate between the two, which is the strong coupling scale for the Galilean. Now that's the strong coupling scale in the sense that perturbation theory, if you compute scattering of gravitons, compute the S matrix for some scattering process, say 2, 2 goes in, something happens in between, then perturbation theory breaks down in the system when the energy becomes lambda, and that's reflected by the fact that the Galilean effective field theory is a non-renormalizable effective field theory whose cutoff scale is lambda. And so in particular, in the concrete example of new massive gravity, we sort of gave you a cubic Galileo. So in that case, it was the action looked like something like this. Over lambda 5 halves in the case of 3 dimensions. Whoop. Let's go backwards. And this is an irrelevant operator in the sense of ordinary effective field theory counting. And you see that precisely because it's suppressed by that scale, then perturbation theory will break down to that scale. So this is the strong coupling scale of the system. However, this strong coupling physics is extremely important for resolving the VDVZ discontinuity. And just to remind you the logic, or at least to phrase it in a different language, so the idea is you want to think about the force between two stress energies, let's say T mu nu and T mu nu prime, then this force is propagated by the massive graviton. But if we think about its contribution in terms of the individual helicities, then we have a contribution from helicity 2 mode, which is h mu nu. So this is capital H mu nu. And that's the one that will give you the ordinary force that you would predict from general relativity, because general relativity is just a single helicity 2 mode. But there's an additional contribution of the force coming from the fact that this Galilean here also couples to the trace of the stress energy. And so there'll be a force between the traces of the stress energy propagated by that helicity 0 mode. Phi. And the fact that we have an additional contribution, which is typically of the same order of magnitude, but couples to the trace rather than T mu nu, will then give you a different answer for the force law between the T mu nus, which corresponds to a different answer for static versus relativistic sources. And this is responsible for the VDVZ discontinuity. But the resolution of the discontinuity is if I actually take a physical system of mass m, so for example, the solar system, whose mass is dominated by the sun in the solar system, then there is some characteristic scale called the Einstein radius, which was given by Planck minus 2 over 2. There's some characteristic scale. Sorry, it's actually called the Einstein radius. Within that scale, so here's the sun, and the Einstein radius for the sun turns out to be about 150 parsecs. So if we assume if we neglect everything else in the universe apart from our solar system, the Einstein radius will be 150 parsecs. And this calculation, the linear calculation that gives the VDV discontinuity, is valid at larger distances. So the weak coupling theory is valid there, but inside the Einstein radius, the theory is strongly coupled. And that means, in a mundane sense, that just means that the nonlinearity piece here dominates. So when I find that if I want to compute the classical potential due to t, this is the piece that dominates within the Weinstein radius, and therefore I was incorrect to use the linear theory, which is what gave rise to the BD discontinuity. And if you like to think in Feynman diagrams, effectively what's going on is, as well as this contribution from the Listy zero mode, you've got the contribution for where you exchange two guys, two Listy zero modes, and three, and so on and so on. And you have to sum up all these diagrams, all the ladder type diagrams, and sum all those up. And even though this individual one is a large contribution, when you sum them up, you get a small effect. So if you think it's like having a series like this, if you look at the derivative expansion of it, it's like that. And so when x is large, you think this is going to be big, but when you look at the full series, when x is large, it's actually a small effect. So it's effectively how the Weinstein is working. The resum contribution from all the Listy zero exchanges actually resums into some negligible correction. And for this system, it turns out to be order of 10 to the minus 12 contribution rather than an order unity contribution. So it's the Weinstein mechanism, and nowadays we refer it as a sort of screening mechanism. There are other screening mechanisms that cosmologists talk about, such as the chameleon and so on. But the screening mechanism is extremely successful in terms of suppressing the contribution from these fifth forces, either the force from the Galilean field. Now, let me give you a little taste of the general structure of Galilean theories. And to do that, I'll just introduce a little bit of math, which you've probably seen before. Let me define the following quantity. So this is a capital pi, I think, which is this double derivative combination of a lambda to the 2 plus t minus 2 over 2. So this is this Galilean invariant combination, because there's the two derivatives here, suppressed by the natural scale you have in particular d dimensions. So it's this quantity whose eigenvalues become order unity at the Weinstein radius, and is small inside is small in the weak coupling region, so at larger distances. So pi is much smaller than 1, for r bigger than Einstein, and then it's much bigger than 1 for r less than r Einstein. But this is it's of course it's an actual tensor, but if you think of its four eigenvalues, those four numbers essentially are controlling the strength of the Weinstein mechanism. And it's a Galilean invariant combination. Now from this tensor we can define the characteristic polynomials, or the symmetric polynomials, which I think we've heard about. And just a reminder, the motivation for that definition is, let's consider the definition of the determinant in d dimensions. Then you can define the determinant using the Levi-Civita symbols. Let me write it like this: A, B, C, da 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 da. Epsilon, A, B, C, da da da. So these are the Levi-Civita symbols. And then you contract the matrix between pairs of the two Levi-Civita symbols. So you have A, B, B, A, C, C, etc., until you've used all the dimensions of the Levi-Civita symbols. So these are obviously d-dimensional, and that's the definition of the determinant. Now the definition of the characteristic or symmetric polynomials, people have slightly different conventions on this, but let me just tell you what I'm going to do, is think about the following. Think about the determinant of eta plus s times capital pi, and expand this in powers of s. Well, it will go up to d, so it'll go up to power of d. And the coefficients in that expansion define the symmetric polynomials of that tensor. And so just by doing the expansion in our definition of the determinant, you can give an expression for those objects in terms of this capital pi. So explicitly, Sn of pi is equal to 1 over d minus n factorial, which just comes from doing expansion, binomial expansion. And then you'll have epsilon a, b, c, d, blah, 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 epsilon capital A, b, c, d, blah, blah, blah. And then you'll have various etas. So eta is the Minkowski metric, so I'm constructing this in Minkowski spacetime. And you'll have d minus n of those contracted with these pairs of indices, this one with, so they have AA, DB, etc., until you have got d minus n of these. And then finally you have the pi's, of which there are n of those. So in other words, in the determinant formula, instead of having d pi's, we're going to replace it by d minus n etas and n pi's. But otherwise, apart from the overall normalization, it's the same type of formula. So just to be explicit about that, if we look at S1 of pi, this is a scalar quantity, and S1 will be by definition linear in pi, and so it's not hard to see that the only object that's linear in pi is just the trace of that object. And S2, when you work it out, is this particular combination, the trace squared minus the trace of the square. So it's the square of the trace minus the trace of the square. Exactly. And so on and so on. And then it gets more complicated at higher order, but this is actually probably an easy way to think about it. So that's one object to think about. I'm going to define another object now, which is that this is a scalar quantity. Now associated with this, we can also define a tensor quantity, which is essentially what we get by varying this with respect to one of the pi's. And so let me define x mu nu n as a function of this capital pi to be, again, the normalization doesn't matter too much, it's just a convention. Put it in like that. And then you have epsilon mu, so the first two indices of each Levi-Civita symbol are going to be attached with the indices of this tensor. And then the rest is the same, except now we have d minus 1 remaining indices. And so we have the etas and then the pi's. And we have d minus 1 minus n of these and n of those. And we contract all the other indices, leaving only the first index here and here uncontracted, so that we have a tensor. So again, just to give a feel of what that looks like, x mu nu 1 of pi is equal to the trace times eta mu nu minus pi mu nu, and x mu 2 is quadratic in the pi's, and offhand it's not entirely obvious to guess what it is. It's the square of the trace minus the trace of the square. Sorry, I should use different labeling there. Alpha alpha, alpha beta times eta mu nu minus 2 times pi alpha alpha pi mu nu minus pi mu alpha pi alpha nu. And so on and so on, and they get more complicated at higher order. But again, this is probably this is the simplest form way to think about it. So these are sort of natural objects to construct. So having defined those objects, that gives me everything I need to write down the most general form of the Galilean theory that I would get coupled to an LST2 mode. So if you take whatever theory of massive gravity you're interested in, and you take this decoupling limit, and you focus on the Listy 0 mode and the Listy 2 mode. The vector is not so important because it doesn't couple to the stress energy, so we can include it, but just for simplicity, let's ignore it. The Listy 1 mode I'm going to ignore. Then the general decoupling limit theory so decoupling limit, remember, is the limit m goes to 0, m prime goes to infinity, keeping lambda fixed. The general form of that theory will have the Listy 2 mode with an Einstein-Hilbert term, written like this, Lish-Nerevitz operator. Then it would have, you can have h mu nu coupled in general to this tensor x mu nu. Let me write this the other way around. Coupled to this tensor built out of capital pi, the Galilean invariant combination, with arbitrary coefficients. On top of that, we could have, this is the ordinary pi, not the capital pi, sum from n equals 0 to the alpha n times the symmetric polynomial. And then plus finally, the generic coupling to matter, which will look like this. So it'll be t mu nu coupled to x mu nu of n I with the general different coefficients than before. And this is the most general effective theory for a Galilean coupled to a single helicity 2 mode that you can write down that respects the Galilean symmetry. So under the symmetry pi goes to pi plus a plus b mu x mu, then s maps into s. So it's a symmetry of the action, but it is not a symmetry of the Lagrangian because here we have pi without the two derivatives on it. So this clearly shifts under the transformation. These guys don't, but it is a symmetry of the action and it's a symmetry of the equations of motion. So the action shifts by a total derivative. An experience shows of just working on the decoupling limit for various different theories that they all fall into special classes of this case. So the new massive gravity case was one of these examples. So although it's written slightly differently, the box pi d pi squared example, I wrote it like that before. It doesn't obviously look like it's of this form, which is pi times the symmetric polynomial. But what you can do is integrate by parts and rewrite this cubic interaction in terms of pi times s2 of pi after integration by parts. So this is a universal form that's slightly, cosmetically slightly easier, written in terms of the symmetric characteristic polynomials and their associated tensors. So let me give you the properties of this action. There are some nice properties, one of which we've already alluded to. Are there any questions on that? Does everyone follow the notation? So it has some special properties. One is the one I've told you, that it's invariant under the Galilean symmetry. That one is straightforward to check. The second property, which is not immediately obvious, but is relatively straightforward to check, is that the equations of motion are all second order. This is despite the fact that the Lagrangian admits double derivatives of the field. So normally you think that if the Lagrangian mixed double derivatives equations are going to have at least cubic derivatives, these third order derivatives, but these are analogs of the Lovelock terms that Rachel talked about yesterday for gravity. These are the Lovelock invariants for the Galilean, which have the property that the equations of motion are precisely second order. So when you do the derivation, you find that all the cubic derivatives, the third order derivatives you might get, all happen to cancel out, and the equations of motion are fundamentally second order. So it's analogous to the Lovelock terms. And of course that's important in terms of the ghost freedomness. It's not that guarantees the absence of ghosts, because absence of ghosts also has to do with the sign of the kinetic term, but it guarantees the absence of Ostrogradsky type ghosts, which are those ghosts that arise from having systems whose equations of motion are higher order. And that that's one of the important properties we require of these theories. The last one property is that here we're thinking of these theories as effective quantum field theories. So I haven't talked much really about anything quantum about them, but these are you can think of these as quantum effective field theories. And all of these operators that I've written down satisfy a non-renormalization theorem. So concretely, what that means is that these coefficients, the gamma n's, the beta n's, and the alpha n's, receive no quantum corrections, at least in this decoupling limit, from quantum mechanical loops of the graviton, or from pi, or from any matter fields which are coupled to pi in a Galilean invariant way. This is not saying that the theory receives no quantum corrections. Of course it does. It's an effective field theory, so there's an infinite number of corrections. What it means is that these particular operators do not get renormalized. And let me sketch why that is true. And it's actually, once you see the argument, it's pretty straightforward. And to do that, let me compute what in quantum field theory is called the one particle irreducible effective action. Which is so I mentioned before about the generating functional, the scalar field theory. Pi is our scalar. We'll just focus on pi. You've got some action pi, then you define the generating functional by adding in a source for pi, and then performing the path integral. And this is the generating functional's function of the source, and that's effectively, in terms of T mu, what we were computing earlier. And then the one particle irreducible effective action is the Legendre transform of that object. All right. You can think of this as the mean field, so it's the Legendre transform. And it's a useful quantity because it basically encodes the quantum corrections.